In this video, I'm going to show how you can use just high school algebra skills to derive calculus-based physics equations. So this way, if anybody ever asks you if you've had very much math or if you know very much math, you can say, well, I've just had high school algebra, but I can do calculus-based physics, where I use calculus to determine things like velocity and distance and such, but then again, can't everybody? There's quite a bit here, so I don't know if I'm going to keep this as one video or divide it up into smaller videos. I'll figure it out later. So one day I was just doodling some derivations for the kinematics, and it seemed like a good idea to organize them and organize their derivations. And then I wondered if I could present this in a fairly short, concise video so that someone with just high school algebra skills could follow along and understand everything. So that's what I'm shooting for here. So I'm going to keep this real simple. Baby steps, step by step. So theoretically, if you just know some high school algebra, after watching this video, you can say that you understand some calculus-based physics. And keep in mind that even though I am taking baby steps, like really small steps on everything here, and it is all based on high school algebra, there's going to be a lot to it. So you may have to watch this video 5 or 10 times or whatever it takes to get all the information. But every step is actually small and easy to understand. It's just there's a lot of steps, so you have to have a lot of patience or determination or both. Starting out, distance over time equals your velocity. So that's your miles per hour, meters per second, or whatever. That seems pretty straightforward. In other words, the more distance you can cover in the shortest amount of time gives you the fastest velocity. Next up, let's graph this distance-time velocity relationship. On our x-axis, we will typically put the independent variable. In this case, this will be time. Time moves along independently, whether we want it to or not. And on the y-axis, we have our dependent variable. And the dependent variable means that we can change it. So right here at time 0, we are 2 meters from the starting line. Then at time equals 10 seconds later, we are still at 2 meters from the starting line. So we haven't moved. This is where slope comes in from basic algebra. Change in y over change in x equals your slope, also abbreviated as m. In this case, change in distance over change in time gives you your slope. But what is distance over time? That is your velocity. Distance over time is velocity. Then we can also take a derivative of distance, which is our y-axis, to get the same answer, and I'll show that. Super easy. I did a couple other videos on derivatives and integrals and how to use them and made them super simple, so see those videos if you want. I did a couple more videos that were a little more complex that showed how to derive those equations, but see the simpler videos if you want. They're really easy. Anyways, distance over time equals your velocity right there, or a derivative of your distance gives the same thing. That all equals your velocity right here. This all equals velocity right there. I just wrote here again, a little redundant, change in y over change in x equals change in distance over change in time. So our distance change will go from 2 right here, 2 meters, and then we subtract 2 meters there, so 2 minus 2 is 0. And then our time will be 10 minus 0. So it's change in y over change in x gives us 0, so thus we have 0 velocity. We can take a derivative right here. You just simply write d/dx of 2, because 2 is our y value. So when you take a derivative, you take a derivative of that y value, which is 2. 2 is the same thing as 2 times x to the 0 power. Anything to the 0 power is 1, so it's just 2 times 1, which equals 2. To take a derivative, you bring that exponent down and multiply it by the coefficient, which is 2. 2 times 0 gives 0. That is your velocity. Next page. Right here, I was just showing, just for fun, I wanted to explore some dead ends. So instead of distance divided by time gives you velocity, what happens if you take distance times time? In this case, this would give you the area of the rectangle here. But as far as I can tell, that doesn't give us any meaningful information by getting the area of this particular rectangle. In other words, I don't think you can really say I walked 3 miles I walked 3 miles times 3 hours. If you multiply 3 miles times 3 hours, you get 9, and you can't do anything with that. But if this was velocity versus time, then you multiply your y-axis by your x-axis, which is velocity times time. That gives you the area right here, and that's called an integral. So I'll talk more about that later. It's super easy also. Next up, let's do another distance-time relationship. What's distance divided by time? That's your y-axis divided by your x-axis. That's your slope. That's also m, and that is also your velocity. Change in y over change in x, 4 minus 0 divided by 2 minus 0. And that gives us a velocity of 2. To take a derivative to get the same answer, your y-axis must be in a form of your x-axis. In other words here, x-axis is time, so we have to put the y value in a form of time. In this case, the y value will equal double your time or 2 times your time. So if your time is 2, then your distance will be 4. If your time is 6, then your distance will be 12. You just double it. So let's take a derivative of 2 times t, because this is our y value right here. This is the same thing as a derivative times 2 times t to the first. Anything to the first power is itself. So what you do when taking a derivative, you bring your exponent down, multiply it by your coefficient. So that becomes 2 times 1. And then you subtract 1 from your exponent, so that 1 goes to 0. So 2 times 1 times t to the 0. Anything to the 0 is simply 1. So it's just 2 times 1, which equals 2. And that is your velocity. The same we got up here by taking change in y over change in x. So just always remember, over and over, I know the derivative is a new thing for a lot of people. M is your slope. It's just change in y over change in x, which is also your derivative. Next page. Now we're going to get a little more tricky. As time moves along to the right, then we square our time to get our distance. So if time equals 1, distance equals 1. If time equals 2, distance is 4. If time is 3, distance is 9. You take the slope to get your velocity, but notice the slope here is very gradual. The slope over here is very steep. We have a constantly changing slope, which means we have a constantly changing velocity, which means we are accelerating. Changing m is changing slope. That triangle means delta, which is changing. So changing m equals changing velocity, which means we are accelerating and getting faster. Here you cannot simply do a change in y over change in x, because here you're going to have a big change in y because it's very steep, and here you'll have a gradual change in y. We just take the derivative of our y value, and the y value must be in a form of the x value. In other words, notice they are both t. So we take the derivative of t squared right there. Taking a derivative means you bring your exponent down, so it becomes 2t, and you subtract 1 from the exponent, so 2 goes to 1. So we end up with 2 times time to the first power, which is just 2t, and that is your velocity. So for example, if our time is at 2 seconds, 2 times 2 is 4, our velocity will be 4. If our time is at 3 seconds, then our velocity will be 6. If our time is at 6 seconds, then the velocity will be 12, because we just multiply time times 2 to get our velocity, and we do that because we took a derivative of it, or of our y-axis. And I just said here that y equals t squared. That's our y value right there. And t squared, by the way, equals the distance. The way you can show your derivative is simply y prime. So y equals your distance. If you take y prime, that's the same thing as f prime of x. You can use either terminology there, and that derivative will be 2t, which is right there, and that'll give you velocity. So y gives you the distance. The derivative of y will give you the velocity. If you take a derivative of your velocity, then you'll get acceleration, and we call that y double prime, or f double prime of x. And I'll show more about that later. So, in other words, the derivative of your distance is your velocity. The derivative of your velocity equals your acceleration. Next page. This is what acceleration is right here. Remember, if you take the derivative of velocity, then you're just taking a slope, which is change in y over change in x. Here we have a velocity of 0 at time equals 0. As that time increases, our velocity gets faster and faster. We're speeding up, so we're accelerating. Take a slope of that. That's the same thing as taking a derivative. So derivative of velocity equals acceleration. The units right here, just velocity over time equals acceleration. Again, change in velocity over change in time. Change in y over change in x, which equals slope. You can rearrange those to time times acceleration equals velocity. So for example, let's say our acceleration equals 2 meters per second. What this is velocity divided by time. Velocity divided by time. This is usually shortened to 2 meters per second squared because it's second divided, or because the second right here gets multiplied by that second. So here's what the little timeline chart would look like. Your time in seconds equals 0 seconds, 1, 2, 3 seconds. Your velocity will start out at 0, then go 2, 4, and 6, because acceleration is 2 meters per second. So every second that goes by, you travel at a faster velocity of 2 meters per second. So 1 second, you're going 2 meters per second. The next second, you're going 4 meters per second. The next second, you're going 6 meters per second. You're accelerating with a velocity of 2 meters per second every second. And next page. Now instead of distance versus time, we have velocity versus time. And that's just what I said right there. Instead of distance versus time, we have velocity versus time. As you can tell, as time moves along, our velocity is increasing, which means you're accelerating if you're increasing your velocity. Take the slope, which is change in y over change in x, which is change in velocity over change in time, and that will equal your acceleration. 4 minus 0 divided by 2 minus 0 gives you an acceleration of 2, and that is the same thing as taking a derivative of 2t. Notice right here I just took time, and I'm going to write right here 2 times time. So whatever value you get for time, you double it, and that gives you your velocity. I'll show how to take a derivative here of the 2t again. Remember, for a derivative, there's only 2 rules. Bring your exponent down, and then subtract 1 from the exponent. So derivative, which is d dx of 2t, that's t to the first power. Bring the 1 down, you get 2 times 1, which is 2. And so you just end up with 2, and I'm going to write it out right here at the bottom. So right here, this is the same thing as 2 times t to the 0, because we brought that 1 down and subtracted 1 from the exponent. Anything to the 0 power is 1, so you just end up with 2, and that equals your acceleration. Because when you take a derivative or a slope of velocity, because derivative and slope are the same thing, you end up with acceleration. Right here, I'm going to show how to take the derivatives of everything to get your values, starting with time on the x-axis, distance on the y-axis. Remember, the value on the y-axis needs to be in a form of the x-axis. So x-axis will be time, the y-axis will be time to the 3rd power. So if time is, say, 2 seconds, then distance will be 2 to the 3rd, which will be 8. You'll have covered, say, 8 meters. Remember, all derivative is slope, which is change in y over change in x. If you graph out distance versus time and you take the slope of that, you'll get your velocity. Then what you do is graph out velocity versus time, take a derivative of that, or a slope of that, and you'll get acceleration. Then you graph out acceleration versus time, take a slope of that line, which is the same thing as a derivative, and you'll get jerk. To take a derivative, you bring down your exponent and subtract 1 from the exponent. Those are the only 2 rules. So for distance, we have t to the 3rd. Bring down your exponent, you end up with 3t, but you have to subtract 1 from that exponent, so it's 3t squared. Take a derivative of this, then bring your 2 down, so you end up with 6t, and that 2 becomes a 1, so you end up with just 6t. That's your acceleration. Take a derivative of acceleration, and you get jerk. And it looks like this here. Your slope will be change in distance over change in time. Here's your distance, here's your time. And that gives velocity. Take your velocity, change in velocity over change in time, gives you your acceleration. Take your acceleration then, change in acceleration over change in time gives you jerk. And then take your jerk right here, change in jerk over change in time gives you snap. I've read and heard in a few places that when it comes to injury assessment, like with car crashes or falls or whatever, possibly jerk is more important than acceleration. So if you fall and hit the ground, it's not the deceleration that hurts you as much as the change of acceleration. But that's all esoteric stuff to that field, so I don't know anything about that. If you keep taking derivatives after jerk, you get snap, crackle, and then pop. But everything I read and heard said that really after jerk and maybe snap, they don't use, the other derivatives aren't really used. Don't know, not my field. And next page. If we want to graph out all of these derivatives, this is what it'll look like. Notice here we have time along the x-axis, distance on the y-axis, which is time to the third power. That gives us this shape right here. I drew a dotted line there because you can't have a negative time. So we take change in distance over change in time. That gives us our velocity. If we graph out velocity versus time, velocity equals 3t squared right here. What this means is whatever your value for t is, you square it and then multiply it by 3, and that will give you your velocity. And then if we want to graph out change in velocity divided by change in time, that will give us this graph right here, which is acceleration of 6t. Then we can take change in acceleration divided by change in time, and that will give us our jerk, which is a straight line of 6. Now we're going to cover integrals, which are just about as easy. A derivative is just your slope, say distance over time equals velocity. That also means that velocity times time will equal your distance. Now we're going to do an integral. Let's graph out velocity versus time. So for 10 seconds, we've been traveling 3 meters per second. We just take x times y, or we take our velocity times time, and that gives us our distance. So x times y equals distance. Our x is 10, our y is 3. 10 times 3 means we've covered 30 meters right there. Notice that when we take x times y, we're taking the base times the height of a rectangle, and we're getting the area of that rectangle to get our distance. This is what an integral does for us. Take an integral of your y value. In this case, our y value is 3. Velocity does not change. We're staying 3 miles per hour, 3 meters per second the entire time. So whatever you do to take a derivative, do the opposite to take an integral because they reverse each other. So for example here, we just draw our integral symbol right here, that long S of 3, because 3 is our y value. Then what we do, we put the dx here just to show we're taking an integral of the x. What this means is 3 by itself is the same thing as 3 times x to the 0. Anything to the 0 is 1, so this just equals 3. dx means we're taking an integral of the x and no other variables, so if we have a, b, and c in here, we ignore those. So for an integral, you do the opposite of a derivative. So instead of lowering your exponent, you raise your exponent so that x to the 0 becomes x to the first. Then you bring that exponent down to a denominator. Those are the only 2 steps. Step 1, raise your exponent by 1. Step 2, bring that exponent down to a denominator. You end up with 3 over 1 times x to the first, which is just 3x. What this integral does, it gives you the area under this line, or an area under a curve if this curves up. And in this case, if you take an integral of velocity, it will give you distance, because velocity times time equals distance. So an integral means you're multiplying the y-axis times the x-axis. Test this out here and see. For example, let's say our x value will equal 10 right here. Take 10 times 3. What do you get? 10 times 3 gives you 30. So 30 meters is your distance. And that is also the area under the curve, or the area under the straight line. Remember, integrals and derivatives reverse each other. So if you take a derivative of distance, you get velocity. If you take the integral of velocity, you'll get distance. And that's just shown by this equation right here as well. Velocity times time equals distance. Taking your y-axis or your y value times your x value to get distance. What the integral formula does right here, though, it allows you to plug in any x value to get your velocity. And taking integral also works if you don't have a straight line, if you don't have a rectangle here. If this is like a curve, like a parabola, then you'll need to do an integral to get that area under the curve, which is the same as getting the area under this rectangle, or the area of the rectangle. Also, since an integral just gives you an area under the curve or the line, if this was a triangle, then you could also use the formula for the area of a triangle, which is 1/2 times base times height. And also notice here, if you take the derivative of 3x, you're going to end up with just 3. I should have wrote that as distance right there. So if you take the derivative of your distance, you get your velocity. If you take the integral of your velocity, you'll get distance. Next page. Remember, an integral does two things. First off, it reverses a derivative. And secondly, it gives you an area under the curve or an area under the line. So in order to get acceleration, we can take a derivative of velocity. Remember, derivative of distance gives you velocity. Derivative of velocity gives you acceleration. So to reverse that, we take an integral of acceleration to get velocity. And what an integral does, it gives us the area under the line. So that means we can simply take acceleration times time to get our velocity. Should have wrote it out here too. If we're dealing with a straight line, we wouldn't have to take an integral. You can just use the formula. Change in velocity over change in time equals your acceleration. So for example, you could go from 10 miles per hour to 20 miles per hour in 1 hour. That would give you an acceleration of 10 miles per hour per hour. But just rearrange our equation so that velocity will equal acceleration times time right here. And we have acceleration times time. That means we're taking the y-axis times the x-axis because we have acceleration on the y-axis, time on the x-axis. You can also get the area under a line here by doing the formula for the area of a triangle. 1/2 times base times height gives the area for a triangle. But we can take an integral of our y value, 6t. So we just do the opposite of what we would do for a derivative. 6t right here, dt means we're taking a integral of just the t. And in this case, we're going to go from x equals 1 to x equals 0. That's what I wrote right there and there. We can actually pull the 6 out since we're not interested in that. We just want the t right here. So the integral of time, that means that is time to the first power. So let's see, I brought this down to here. Time to the first power, that means that one exponent has to go to a 2. Then you bring the 2 down to a denominator. There's only 2 steps for an integral, and that's it. You raise the exponent to 1, then bring the new exponent down to a denominator. So that t to the first becomes t to the second, bring it down. So you get 6 times 1/2 t, 6 times 1/2 t squared. 6 times 1/2 is 3, so you end up with 3t squared. This is also the same thing as acceleration times time, and that gives you your velocity. Next page. This page right here will just be to show how to derive something the wrong way to get the wrong answer. Skip past it if you're not interested, but I like to explore all the ends, including the dead ends. Distance over time is velocity, as I've covered, which means distance equals velocity times time. This does not work with acceleration, though. Also, another equation, change in velocity over change in time equals your acceleration. Thus, velocity equals acceleration times time. So does that mean wherever we have a velocity, distance equals velocity times time? Wherever we have this velocity, can we just plug in acceleration times time? Let's see what happens. Distance equals velocity times time, just like I showed up here. For velocity, let's plug in acceleration times time right there. We end up with at squared, and that does not equal our distance. The reason is because our velocity is not constant, it's changing, so we need an average velocity. So we use calculus to derive the next equation. But I'll show how to do it in a non-calculus way first. As I showed, velocity times time equals distance, but that's our average velocity. To get that, you just get your initial velocity times your final velocity, divide it by 2. To get your average velocity, multiply that by the time, just bring that down. Now you got your distance. This is the non-calculus way to do it, and next page I'll show the calculus way to do it. Here we have a velocity versus time graph, And what happens if you take the slope of this line? That means you're taking a derivative of velocity, which will give you acceleration. Here's the equations. Change in velocity over change in time equals acceleration. So therefore, acceleration times time will equal your velocity. So up here for velocity, I just write acceleration times time. Next equation, distance over times velocity. So therefore, velocity times time equals distance. If we take a derivative of distance, we get velocity. So let's take the integral of velocity to turn it back into distance, because derivatives and integrals reverse each other. So velocity equals acceleration times time. So let's take an integral of that. Acceleration times time. dt means we're taking an integral of just the t, so we can pull the a out of the integral sign. We don't need that. And again, an integral of velocity will give us distance. So for the integral, you just raise your exponent to 1 and then bring it down to a denominator. That means t becomes t squared. And then you bring that 2 down to a denominator. So you end up with acceleration times 1/2 t squared. And then for technical reasons, you add c. Rearrange this equation right here and you get distance. By the way, all of this will equal distance. Rearrange the equation. Distance equals 1/2 at squared. And then you write plus c for technical reasons. And the reason for that is derivatives and integrals reverse each other. So c means the same thing as c times x to the 0. Anything to the 0 power is 1. So since we took an integral of velocity to get to this point, if we want to take a derivative to reverse it, you just bring your exponent down there, multiply it by c, and you end up with 0. And since we took an integral to get this 1/2 at squared, we can take a derivative to reverse that. To take a derivative, bring your exponent down and subtract 1. You just end up with at, which is right up here, which is velocity. So since this all right here equals distance, we take a derivative of distance to get our velocity, and we took an integral of our velocity to get our distance. And this brings us to the final form of our equation. Distance equals 1/2 at squared plus c. c will be our initial distance. So we end up with our final distance equals 1/2 at squared plus initial distance. And if we wanted to, we could even convert that initial distance to initial velocity times initial time. So if we went 5 miles per hour for 5 hours, then that means we've covered 25 miles, and we add that to whatever we get right there. The final equation I'm going to derive is this one. Velocity times time equals your distance, but if you have a changing velocity because you're accelerating or decelerating, you just take your final velocity plus initial velocity, divide it by 2 to get your average velocity times time gives distance. Next equation will be a change in velocity over change in time is your acceleration. You can imagine if you rapidly change your velocity over a short period of time, you'll have a rapid acceleration or deceleration. This also means velocity over acceleration equals time when you rearrange that equation. So let's put this equation here in a different form. Final velocity plus initial velocity divided by 2 comes down to right here. And then where we have time right here, we replace that with velocity divided by acceleration. Or I should say change in velocity over acceleration equals your time. So that'll be final velocity minus initial velocity divided by acceleration from right here. So we multiply this by this by this to get our distance. Go through the algebra right here, and you'll end up with v final squared equals v initial squared plus 2 times AD. Also, I could not come up with this final derivation on my own, because this one right here was pretty tricky, and I just would not have guessed that that would have worked. So I had to get this derivation off the internet. So that's it. If you were able to sit through 25 or 30 minutes worth of videos explaining this, you can now say you understand calculus-based physics when it comes to kinematics, or kinematic equations, which just means it's the equations that describe motion.